Okay, good. I think we're going to start this workshop. I'd like to welcome all of you to CSCS. I don't know if this is your first time at CSCS or if you've been here before. Anyway, perhaps at lunchtime we'll have a few minutes to show you around the building. Those are the offices in this building here, and then on my back is the big computer room. You know that CSCS hosts some pretty big supercomputers here. And this is what we're here for. It's actually to learn how to couple simulation codes with visualization infrastructures. Good. My name is Jean Favre. I'm here at CSCS since over 20 years, and I've been doing visualization for all this time. What does that mean? It means that I have put my hands, so to speak, quite a bit into the visualization libraries, and mostly the VTK library, which is at the base of two open applications, as we know, open source, VisIt and ParaView. So VTK is the toolkit, the C++ tool, the original C++ toolkit, which serves as a back end to VisIt and ParaView. And on this, I've built up quite a lot of experience in different fields. Of course, most often in the traditional simulation fields of supercomputing centers, such as fluid dynamics, astrophysics, climate, geophysics, etc. So this is the experience I bring here. It's really a day-to-day experience of applying those visualization tools. And because we are in the supercomputing centers and we tend to do big data, my experience is also quite a bit on large data and on parallel deployment of the open source software. So I actually put a lot of emphasis and focus on delivering solutions which are parallel enabled. That's really the principal focus of my efforts. Let me introduce Berlin Loring from Lawrence Berkeley National Lab. I'd like to really give a very warm welcome to Berlin, who comes here specially from California to do this workshop at CSCS. So we are really grateful to have him here. Berlin has more or less the same experience as I have, in the sense that he's a developer. He's been very active in different facets of visualization softwares and architectures, again, related or based on the VTK toolkit. Berlin now is active in the SENSEI project, which is going to be the focus of our workshop today and tomorrow. The SENSEI project has recently passed a 3-year deadline, which I think was the first phase. Is that correct? The first funding phase from the US funding agency, and it's now on its second phase of funding, which is a good sign. It means the project has actually proven already to be a very viable approach. Now, this tutorial has been given for the first time at Supercomputing last year in Denver. Was it Denver? Yes, I was there, yeah, I remember. So in November, if I try to recall all the names of the participants, of the teachers, perhaps Berlin, you can help me. Wes Bettel, yes. Andy Barrow from Kitware, Silvio Rizzi from Aragon, for the ADIOS part,
Matthew Wolf.
Matthew Wolf, and what was the last person? I forgot now that last person's name. Anyway, this tutorial has served as the initial phase of the effort, and I was so pleased with the output of the tutorial, which I attended as a participant, that I propose to repeat this at CSCS. Now, the initial tutorial at Supercomputing was a half-day tutorial, and I found that extremely frustrating. There was way too much material to show in a half day. So this is why today and tomorrow, we're going to try to stretch that to a comfortable 2 days of material, so we will have time to actually do exercise, do demonstrations, and then since we have a small group here, I actually like this, we should be able to, between Berlin and I, to actually divide ourselves among you and answer really specific questions you might have about your particular simulations. I'd like to say that as far as the previous in situ solutions that are now available as of a few years, VisIt as a toolkit, or rather a library called Libsim, with which I've gained a lot of experience already in the years 2011, I think, when we published a paper at EGPGV on the Libsim. So Brad Whitlock is actually a contributor for the tutorial. I forgot his name earlier. Brad and Jeremy Meredith from Oak Ridge were the people who had contributed to that effort. So I had originally gained quite a bit of experience with Libsim. Then perhaps more or less the same year, ParaView expanded its portfolio of algorithms and techniques and interfaces with the so-called Catalyst plugin, and Catalyst served exactly the purpose of doing the in situ visualization. Now, with VisIt Libsim, we had to use a dedicated API for Libsim, right? We're going to see what they are, the data bridges and data adapters specific to that API. And then if one wanted to switch to the other in situ library, we had to do all the work again. So learn a second API, develop the code for a second API, and so forth. And then the same thing you would have to do if you wanted to use, for example, ADIOS, or other layers of interface. So there comes the idea for SENSEI, and I'm going to let Berlin do more of the introduction in that sense. It's really to have an umbrella interface over those multiple toolkits, such that you learn one API, you develop one code with that API, and then you can use multiple backends for the in situ visualization. So this is really the philosophy that we're going to develop and demonstrate during those 2 days of tutorial. Okay? So Berlin, you want to take over?
Sure.
Yep.
Thanks, John.
Yep.
Thanks for the great intro.
Yep.
Just want to mention, as John had just said, that the tutorial is developed by a number of people. The SENSEI team, we've got people from Kitware, Catalyst experts. We've got Andy Bauer, Utkar Shayashit, Patrick O'Leary. On the VisIt side, we've got Brad Whitlock on our team. We've got some ADIOS developers. Matthew Wolf at Lawrence Berkeley Lab. We've got Gunther Weber, Wes Bethel, Dmitry Morazov, and myself. At Argonne, we've got Silvia Rizzi, Nicola Ferrier, and Venkat Vishwanath. And so we also have Intelligent Light, which has another visualization tool and does a lot of CFD. And from Intelligent Light, we've got Earl Duke. So we've got a pretty diverse team, and at all of the stakeholders, we've all partnered up with science teams. So we actually have some use cases that we're applying SENSEI to. So we not only have the computer science side, where we're designing and testing and researching different parallel design patterns and use cases, but we're also applying it to a broad range of science use cases, laser plasma accelerators, climate science, molecular dynamics, CFD, and I'm trying to think, that may be the extent of it currently. And so this, as John mentioned, this tutorial was given at SC17, but we've expanded it. And we hope that you'll come away with the practical skill set to actually go out and apply it. Some of the expansions come in looking at the data model that we use as VTK. So John developed a number of exercises. And actually also delving in a little bit to some of the backends, VisIt Libsim, ParaView Catalyst, ADIOS, and actually writing some SENSEI code in the end. And so the exercises and demos are partially in Python and partially in C++, so hopefully you guys are good with that. And you'll get a chance to do some of that. So, the outline of the tutorial, basically we're going to introduce and review in situ visualization, where we've come from, where we're at. We'll look at the SENSEI interface. We'll go into detail about instrumenting data sources and endpoints with SENSEI and C++. Then we have a number of demonstrations from the team members demonstrating various backends and use cases. We've got a Libsim demo, a Catalyst live demo, ADIOS demo, and we have a Python demo as well. And so this slide was from the SC17. John has developed a demo for this tutorial using a Jacobi heat solver, and so we'll also look at that. And finally, we'll look at the cost of doing in situ and the performance you could expect. How much does it cost to instrument your code with SENSEI? How much does it slow you down? And wrap up with some final thoughts. I'm also going to throw in there information about what we're doing in the current round of funding, the SENSEI 2. So as long as we're talking about the VM, I know it seems like it's a hassle to set it up, and I kind of think that maybe if people are having trouble maybe at the break, that maybe Jean can put it on some local system so we could just SCP it over. Apologies about that, but before we need to do anything with the VM, we'll deal with those issues. And so in the VM, we can come back to the slide once we start using the VM if necessary. But so all of the stuff from the supercomputing tutorial is in home SC17. There's two folders there, software and demos. So the demos from the tutorial are in demos. The software, all of the installs, including the source code and builds, are in there. And on the VM, we're using modules. So whenever you want to use ParaView, VisIt, VTK, whatever, you've got to load a module. If you load up the SENSEI modules, we've got SENSEI Libsim, SENSEI Catalyst, and SENSEI VTK. These will configure the environment, for use with the respective backend. And you can also, let's say, if you load the Libsim backend, you can also start VisIt. If you load the Catalyst SENSEI module, you'll also be able to run ParaView. And then, so finally, for this tutorial, we've added a bunch of demos and exercises, and those are in the home CSCS folder. You'll find within home CSCS, there's an in situ folder that has a number of different folders in it, and we'll go into detail later. Once the VM's installed and running, because we have some new material in the CSCS folder that's actually didn't make it onto the VM by the time I froze it, we'll have to CD in there and do a git pull to update it. And just for reference, there is a password on the VM and the password on the VM is cscs_password. If the screensaver kicks on, you'll need to know that. It also gives you root, and also be aware that the VM is live to the outside world. So if you just leave it running on your computer, it will be like another computer on your network. So it's open to hacking or whatever. So just be careful and be aware that that will happen.
Well, I'd like to add the fact that the repository here will remain active even after the tutorial, okay? This is intended to be a source of, a repository of source code which is going to grow for several years, we hope. So nothing is going to be closed, shut down after the end of the week, okay?
Yeah, and I want to actually co-opt your Jacobi mini app and
good.
Start using it, and see if we can use that in Sensei. So Jean, before we go on, like if people are having trouble with the VM, could you put it onto a local machine, do you think, so they could SCP it? So is everybody, so where are we at with the VM? How many people have it successfully going? Okay. The question is, how many people have the VM going? And it looks like just one. So you're working it. Has it like outright failed for anybody, or is it just getting the files? Okay. Okay.
Okay.
While I'm doing this, could you put the file on the local networks?
Yes.
Okay. Okay, we'll come back to the VM slides so that you can update it later, because not everybody is ready anyways. So, welcome, why are we here? Good morning. The problem that we face is that flops, the capacity to generate data and the floating point throughput of supercomputers is growing much, much faster than the capacity for I/O. The problem with that is that there's a potential for less science, in addition to all the practical matters of managing all of that data. So the approach, can we do as much processing as possible with the data still resident in memory? So you reduce the amount of data movement. You get access to everything that you compute, rather than what is possible to save with limited I/O resources. So the point of the tutorial is to inform about the issues, to learn about the technologies that are available and how we can use them. So there's simply not enough I/O bandwidth on the current HPC systems, and the trend's just getting worse. Not enough I/O, you just can't write the data, so you can't analyze it, and that's a problem for science. It's also very energy intense to move this data, to write it to disk, to store it, to maintain it. And there's a real opportunity with In Situ for improving science outcomes when you have access to the full spatial temporal resolution data. So this chart illustrates the problem graphically. There are 3 levels in the chart, or 3 levels of detail. Each one zooms in. So on the top level, where the width of the chart shows the computational bandwidth, or the width of the chart is all about the bandwidth or throughput in terms of petabytes per second or gigabytes per second in the terabytes per second, as the case may be. So the top layer shows the computational bandwidth, 100 of Titan. So Titan is a system in the USA. It's the largest supercomputer in the USA currently. This year, I believe, it's being replaced by a machine called Summit. It's quite a bit larger. So we have 125 petabytes of computational bandwidth on Titan. The on-node memory is only 4.5 petabytes per second. So that's a order 2 reduction in the amount of data that you can move or consume. So on the second layer, we zoomed in yet again, and the width here is the 4.5 petabytes per second, the on-node memory bandwidth. When you go from the on-node memory to the network interface, it's another order 2 loss in bandwidth, down to 24 terabytes per second. Then when you start moving data to disk on the third layer, we've got we're zooming in yet again. We've got shown the width scaled out to the 24 terabytes per second. And so going from the interconnect to storage, you're losing another order of magnitude. So there's a 5-order magnitude on this machine Titan, currently the fastest supercomputer in the USA, of difference between what you can compute and what you can store. And the problem's not going away. Summit is the replacement to Titan. So I think Titan is about 23, it's in the 20s, mid-20s petaflops. Summit is 200 petaflops. It's due to come online this year in 2018 in the summer. When it comes online, it may well be the fastest supercomputer in the world. So with Titan as the baseline for computational throughput, Titan is going to be 5 to 10 times faster and 5 to 10 times more computational throughput. However, the I/O throughput is approximately the same, 1 terabyte per second to disk. We have more disks on Summit, but the amount of data that you can move is remaining about the same. So what is In Situ? There's 2 use cases or 2 models that we think about. So post-processing or post-hoc is where we save the data to disk first, and then later in a separate analysis or viz program reads and processes that data. And that's what we all know and are familiar with. The simulation runs, saves its results to disk, and then later somebody comes back, uses a viz tool, opens up that whatever data is on disk and does their thing. In Situ, we want to process the data as it's produced without writing it to disk and reading it from storage. It's processed in place, and that's where the name comes from, In Situ. There are many flavors and terminology associated with In Situ, which we'll delve into a little bit. Different scenarios, different ways of looking at it. But in the end, the practical view of this is, anything that we can process without writing all of the data that we're processing to persistent storage. So this little diagram or schematic gives you the mental model that you can think about. So here we've got 4 compute nodes. Each compute node has 4 CPUs on it. In this picture, we're thinking, okay, the simulation is running on 3 of the cores, or 3 of the CPUs on the node, and the In Situ or in transit is running on 1 of the cores. In transit is another terminology, another term we're going to talk about and look at. Data is moved from the simulation. The simulation and the analysis do not share the same memory space in the in-transit case. So with In Situ, there's no data movement. You can share memory. You can give a pointer. In transit, we're actually going to move data across the wire. The simulation and the analysis don't share the same memory space. But it's much more interesting than just in situ versus in transit. There are many different ways you can look at this. Once you start thinking and analyzing all of the different scenarios, you can look at it from an access point of view, whether the simulation and the analysis can have direct access to each other's memory, whether that they don't and that data has to be moved. You can look at it from proximity, on node, off node, same computing resource, so you're on the same cluster, or distinct computing resource, you're on a different cluster. You can look at from the perspective of integration, whether your simulation has to be application aware. I've seen one in situ method that uses GDB, and the program automatically tries to figure out a simulation's arrays through GDB. It's pretty neat. So the code, no changes to the code whatsoever need to be made. And this program just automatically looks for things that look like multi-dimensional arrays and starts visualizing them. So that's yet a totally different use case than we're talking about, where we have an API that the simulation knows about and kind of drives. There are other approaches where they look at the actual memory laid out program and try and infer or detect some patterns that let them say this is a three-dimensional array, and they start visualizing it. You can look at it from a point of view of control, automatic or human in the loop. So with automatic, everything happens once you set it up. It just runs and goes. With human in the loop, the human might be looking at the simulation as it's running and then making some changes to the simulation code as he sees the results. So there are many different ways you can look at this problem. We're just going to talk about in situ and transit, but there are many different ways of analyzing this and looking into it. So that's our term in situ is an umbrella for all of these different cases. And this chart comes from Hank Childs, who's one of the developers of VisIt, and he's trying to just think about all the different ways you could describe this problem. In Situ's been around for a long time. Our project leader, Wes, has been at Lawrence Berkeley for 20 years. He's been doing this for a really long time. He came up and did some research into the history of In Situ, and he found the first In Situ use case he found was from March of 1964. The scientist was analyzing the orbits of a satellite, and rather than write the results of his computer simulation, he rendered them direct to film through a calligraphic display. It is in situ. The data never went to disk. Why did he do it? Well, it makes sense. Back in the day before you had dedicated tools like ParaView and VisIt, dedicated viz libraries for this, if a simulation developer wanted to do some analysis and visualization, the easiest thing for him is to write it into his code. And so In Situ has been around for a long time. I'm not going to show the movie. There's a link to the movie if you're curious. In the 1990s, we've got the golden era of coprocessing. So coprocessing, your simulation is running, and while it's running, you've got some visualizations you can do. So it's very interactive coprocessing, where your simulation's running, you can interact with the data as the simulation runs, you can pause the simulation, do things in your analysis, restart the simulation. This is still popular for small codes that run very quickly. It becomes harder and more problematic and it's not practical to do on very large supercomputers like Pittsdent and other large HPC systems. So there's a whole bunch of packages from this era, PV3, AVS, Cumulus. I don't know much about these packages. In the 90s, many different parallel design patterns were explored and developed. Many to one, AVS used that. Tightly coupled. Loosely coupled, M to N, where you've got, whenever we talk about M to N, we're talking about the simulation running on M compute nodes or processors, and the visualization analysis running on N compute nodes or processors. So, with this picture, just the point of this is that, parallel design patterns in situ has been explored for a long time. So if you can think of a parallel design pattern, it's been done. Computational steering is where you throw a human into the loop interactively. So as your simulation runs, there's going to be a human. The human can stop the simulation, interact with it. So the example where this is potentially useful is in protein structure prediction. It's a NP-hard problem, so you're not going to solve it computationally. So what if you allowed a human to enter the loop and kind of an expert come in, be able to kind of refine the simulation as it runs, lets it progress, get unstuck from local minimum, and then resume the calculations. And somebody did this. Nelson Max is the guy in this picture. He's one of the viz researchers at Lawrence Berkeley. He's retired now. So this was done in 2003. So integrated computational environment. So this picture is all about in transit. In transit is where the simulation is running on one set of compute resources, and your visualization is running on another set of compute resources. And the data gets moved across the wire. So this has been done. This picture comes from an SE, a supercomputing bandwidth challenge, and they used the simulation integrated computational environment where the simulation ran on a supercomputing cluster, and the data was shipped over in transit to the supercomputing conference floor, and they did the visualization analysis over there. Another concept that's really useful is explorable extracts. The idea is that one of the main challenges with in situ visualization is that you have to set this up before the run. And you don't really know how it's going to look before the run. You have some idea. You may be able to set up a mock visualization where you can kind of get the parameters mostly right or close. But when you actually do the compute run, you're going to be processing data unseen. You're going to be setting up the visualization, the transfer functions, the color maps, the lighting, the camera angles, all with the data unseen. So that's a challenge. You may not get it right, and if you get it wrong, you may have to redo the run or just live with a suboptimal visualization. Explorable extracts overcomes that. You do some subsetting of the data. Maybe you compute an isosurface. Maybe you do some kind of feature detection and subset the data, write out a much smaller amount. But then with that extract, you can fine-tune the visualization. You can fine-tune the transfer functions, the lighting, the camera angles, and so on and so forth, and get that perfect visualization. So this has been around for a while as well, but it's also very, very relevant. So here's the recap. 1964, the earliest in situ that we could find. 1990s, a lot of code coupling, computational steering, human in the loop. 2000s, integrated computational environments, in transit. 2000s again, you've got extracts, people are doing that. Present day, as Jean mentioned, there are a number of solutions out there. We've got Libsim, Catalyst. ADIOS is another one focused at the I/O layer. Doesn't provide any visualization capabilities, but it provides a lot of flexibility in terms of data movement, getting things in and out. It provides analysis capabilities without any rendering capabilities. And finally, we have SENSEI, which has the generic In Situ interface. Our idea with SENSEI is write once, run everywhere. And there are other In Situ projects starting up. The biggest one that I know of outside of SENSEI is an exascale project targeted at using VTK-M. So there's competition. Okay, so in terms of the SENSEI tutorial, the infrastructures that we're going to look at today, mini apps. So the mini apps in SENSEI are small programs, either simulations or simulation-like programs that generate data and illustrate how SENSEI is used. We've also used them for benchmarking, and we have them in C++ and Python. Simulation codes, we're going to show LAMPS, which is a molecular dynamics simulation, coupled with Osprey, which is a ray tracer. And we're going to show AVF Leslie, which is a CFD code doing computational extracts. These mini apps and sim codes are going to pipe data through the SENSEI interface. And on the back ends, we're going to use ADIOS, Catalyst, Libsim, and some other custom endpoints or analysis tools. So in SENSEI, we provide the endpoints or analysis back end to configure Catalyst, Libsim, and ADIOS so that you don't have to write any code to use those. You just provide the configuration, say a Python script or an XML file. And you can use Libsim, Catalyst, or ADIOS with no coding. But then what if you want to do something else? What if you want to do something really specific that's not in any of those, like you want to do a topological analysis or some computational geometry or something, and there's a really great tool out there. Well, you can develop a new backend, and we have an API for doing that. It's really simple. Our data model allows you to get that data seamlessly and then do what you want with it. And so we're also going to show how that's done and demonstrate it in a number of ways. So the generic view of what's going on from the simulations perspective, and these three stages show what's going on in the simulation code. So this is what the simulation does to do the analysis. So first thing, it initializes the analysis, and then it repeatedly gives it some data and tells it to do something with it. And then when it's done and it's ready to shut down and end its run, it finalizes. So this is what you need to do in your simulation code to use SENSEI or any of these backends. You know, the middle stage is what we're going to be focused on, processing that data. It could be as simple as computing something like a histogram, or it might be something as complex as sending the data over a network to another job that's running Catalyst. So for future reference, this website does have the CSCS tutorial and the original SC17. So the VM is up there, the slides are up there. You guys have all that. And with that, that's the end of the introduction. And now I'm going to switch things over to Jean to talk about the VTK data model. VTK is really at the core of Sensei. So the Sensei provides a few different things. So the Sensei provides an API for accessing data from an analysis code. It provides an API for a simulation to invoke an analysis code, and it provides a data model. And the data model we use is VTK. So VTK is the lingua franca, or the packaging of the data. It's how we package it generically so that the simulation can give data to an analysis. The analysis can access that data without knowing anything about the simulation. So this is one of the things that we want to expand on from the supercomputing tutorial to give folks a better idea of how to package their data in VTK.
Thank you, Berlin. So just as a parenthesis, I've copied the OVA file to our local file system here at CSCS. It's on Pit's date, on my Scratch partition, so you know the standard path name is Scratch SNX 3000. G5 is my username, and the OVA file is called sensei-cscs.ova. Now, for those of you who have already an account on Date, you're all set to go. If you don't already have an account, I have brought with me, I don't know where they are now. Oh, there. Sorry about that. I've brought with me a list of course IDs, so usernames that you can use to log in onto our system. So please, you can circulate this sheet of paper, take the first account on the list with the password, make, I don't know, a line over it with your name, for example, so that we remember, and then the next person takes the next username available. This will give you access to the Pit's Date machine, okay? And by the way, for those of you staying here for the Friday course, those are the IDs that you will use for Friday. So please keep them in line, okay? So those for people who don't have account on Date already. Yes?
If you have an account on Date, we don't need them, right? We need them in the
Yes, you still need them for Friday because we have a reservation of compute nodes for those specific user ID, such that we won't have to wait on the queue, okay?
So before we go, though, is anybody having trouble with the VM that needs to be solved? Do people have it working now? Okay.
Very good.
Awesome. If anybody has any problems, just raise the hand, and we can deal with this. Yes, you don't have the VM.
I have VM, so I downloaded it like last night.
You download? Oh, perfect. So, okay, so what's up?
So I have some error message here.
Let's take a short break.
Yes. So change the network settings.
Okay, to
All right, so just to be clear, just for today, you don't specifically need the usernames, the new username. If you have access to Date, you can just copy the file and you're done.
And it should go from there.
Okay, we'll start again.
So Jean,
Yep.
because we have to update the repo,
Yes.
the CSCS
Yes.
In Situ, should we do that before we start? Since everybody seems to have a VM going now.
Yes.
And then we'll go back to the VTK data model.
Yeah, of course, yeah.
Okay. So let's go back to the slide now that everybody has the VM. So once you have the VM booted up, you should open a terminal, and then you can CD into the CSCS In Situ folder. This is a Git repository. And then you can do a Git pull rebase to pull in the latest versions of the examples. And because Jean's examples are in that that folder, some Python code. So
I not connected to the Wi-Fi. You have Wi-Fi CSC?
Ah, the Wi-Fi connection. Yes. The password to the Wi-Fi, to the public Wi-Fi, is CPU plus GPU.
All
Here, okay?
lowercase.
Lowercase, so
Yeah.
the plus sign, CPU plus GPU. And that should get you on.
C,
Yes.
yes. CPU
Yes.
plus GPU. Two
Do
plus.
you all
plus.
see that Wi-Fi address?
Oh, the name of the network.
It should be
It,
CS.
it should
be
CS.
CS, yes.
Yes, yes. And if anyone gets stuck with this step, just let us know right away.
So do we need to connect to that Wi-Fi or can we go on
Well, yes, to update the VM.
Yeah, you have to have some network connection.
Yeah.
but any network is fine.
Any
Yeah,
network's fine,
sure.
yeah.
Okay, very good. Any other questions? All right, I will move on to the VTK data model then.
Okay.
So what's the difference between the two?
Oh, this is next slide.
Oh, okay.
Okay.
Cool. Very good. So perhaps I should take a little survey of the group
Do you
here.
do you need the slide? Yes. Yes. Okay. So I'm going to write it up here.
Oh, okay. Yeah, I'd like to take a little survey of the group here, since we are a small group. How many of you already programmed with VTK? One person. I knew about Alessandro. Okay, indirectly, yes. Okay, otherwise the rest of you have limited knowledge of VTK. Good. See, this is actually exactly what this lecture will be about. It's going to give you a look at the internal data structures of VTK. Because the reason is, to be able to interface your simulation code with the SENSEI API, we need to understand the VTK data model. That is really the requirement of this effort. Now, VTK is a huge toolkit. I don't know how many C++ classes there are now.
Hundreds.
In hundreds, yeah. VTK is over 20 years old, okay? I was recalling with Berlin this morning that I recall a visualization conference in the 1990s talking with Will Schroeder, who has been president of the Kitware company for many years and is now a senior strategy scientist. I forgot exactly his title. Anyway, Will Schroeder is one of the 3 original authors of the VTK textbook. VTK is huge. We're not going to learn everything here in half an hour, but we need to learn the basic structures of. I've selected 3 types of meshes which are of common interest. The basic Cartesian grid, which is, let's say, in three-dimensional, a three-dimensional block of data with equal spacing in all directions. It's really the simplest grid type you can have in 3D. Then, for example, for the people doing climate, meteorology, we often have grid configurations where in the Z direction, which is the altitude direction for atmospheric science, we use different spacing of grid points. As close as we are to the surface, we use a very fine grid, and then as we go to the upper atmosphere, we use larger spacing. So those type of grids are called rectilinear. Now, in the case of a rectilinear grid which actually follows the topology of the terrain or follows a geometric body, here the coordinates of the grids have to be fully given, have to be explicitly given, and this type of grids we call a structured grid. So the VTK structured grid is actually in some other terms, I think also called the curvilinear grid. And then there is the whole series of finite element solvers, which use elements such as the tetrahedra, the hexahedra, the quadrilateral, etc., etc. Those are called the VTK unstructured grid. And we're going to learn with a simple example how to build a VTK unstructured grid. And using those three types of meshes, the strictly regular Cartesian grid called VTK image data, the rectilinear grid, and the unstructured grid, will have a pretty good idea of how the mesh types are being built in VTK, and then how we attach data, scalar field, vector fields, etc., to the mesh. All right, so it's kind of the motivation for this lecture is about, first of all, describing VTK pipelines. Now, what do we call a pipeline? A pipeline is really a series of modules which we connect together from a data source to an image. And all the data processing that takes place in the middle is the data pipeline. We're going to see this in more detail with the following slides. Then there's something that happened a few years ago now. I forgot exactly the timing, but there was a very nice effort done by Kitware to actually enable the interchange of Python NumPy array with the scalar arrays of VTK. And this has been, as far as I'm concerned, I've followed VTK for 20 years, as I told you. This, for myself, was really a fantastic improvement in the interface, such that you can manipulate data arrays in your traditional Python fashion, very flexible, and then you can feed those arrays directly into the VTK grids. I find this absolutely exciting and fun to work with. So we're going to experience that. We're going to see a few examples of a VTK pipeline. Now, I have to make the distinction between two different things. If you take ParaView, which is the end user application, ParaView also has an executable called VTK Python, which is basically a Python wrapper which gives you access to the Python wrapped method of the C++ toolkit. And most everything now is really available directly from the Python interface. And as far as tutorial and teaching introductory concept to an audience, I find the Python interface really absolutely wonderful. And you don't have to be a Python expert, absolutely not. We're going to show really some simple things which anyone can follow with a basic computer science background. And then we're also going to write ParaView pipeline. Now, the Python syntax there is a little bit different. It's actually easier. It's more user-friendly. So as a first contact with the application, the ParaView Python pipeline is really the easiest. And through the exercise of coding data in the so-called Python programmable source and filters, we're going to be able to read data from disk, for example, and then manipulate data within the ParaView interface. So any of you have used the Python interface to VTK? No. OK, so that's very good. We're here to learn those things. Now, if some of you already know NumPy in Python, you know that you can do a gradient of an array. However, if you don't know what is the underlying mesh, that doesn't necessarily have the sense that you want to have for the calculation of your gradient. So the advantage of tying together NumPy and VTK is that the VTK data model is aware of the mesh type and the cell types underneath, and can actually calculate the correct gradient for your given mesh configuration. So this example, which I've taken from a series of blogs which Berg Javici of Kateware wrote a couple of years ago, this is one of his comments, really motivates the distinction between the two. In NumPy, you'll have a gradient, but if you use the gradient calculated by VTK, you'll get a more accurate gradient computation. In 2013, Ken Moreland, who is also a great actor in the visualization developer scene, Ken is at SENSEI, am I right? Yes, SENSEI. Ken wrote this article in the IEEE Viz transaction, which I liked a lot. It's a survey article, very easy to read. It describes the visualization pipeline, and he gives very simple definitions. So here I have the example of a pipeline: read some data of any type, really, do an isosurface computation, and do an image. That's the most trivial pipeline we can imagine. And really, it's a data flow network which connects together different executable, the reader interface, the filter here, which is the isosurface computation, and then finally what we call the sink, because it's where the data actually, that's the final destination or the final product, if you want. It's making an image or calculating a number that would be your final product. So the modules, functional units with 0 or more input ports. For example, a reading module does not receive input from another executable. It simply reads data from disk. So that would be called a 0 input connection, as opposed to the isosurface filter here in the pipeline, which takes as input the scalar field from the module above. So this would be one input into the isosurface filter. And then we have to make the distinction between execution management. You can have architectures where the flow of data is event-driven or domain-driven. In VTK, we can actually mix the two modes. Now, domain-driven would be the case, the standard case of the rendering module here, when, for example, I change a time step in ParaView, the viewing module updates the time step requirement, if you want, the request, and then it triggers the execution of the whole pipeline above it. We're going to see that in more detail. Now, this visualization pipeline, of course, we're here in a computing center where we produce big data. We often do this in parallel. And this pipeline is often simply, oh, actually, I'm ahead of myself. Wait a second. I'll finish the argument. The pipeline is most often duplicated between the data partitions that your parallel execution server is going to provide, with the option that sometimes filters will actually communicate between each other. The example I've made here of ghost cell generators would be the example where you have two different partitions of the data on two different processors, and to be able to compute a gradient, for example, you actually need the ghost cells from the neighbor processors. Okay, so this would be the case of an exchange of a communication in between filters. Another case, which is very common in ParaView is the final stage of the pipeline where each of the render which do a partial image of their data partition. For the final image, we actually need to merge all those images together. There are different techniques for that, and ParaView does this under the cover for you, but there's really communications between all the renderer at this level. But let me go back to the previous slide. Now, the VTK execution module actually works with 3 different phases of executions, and those are fundamental to understand as we're going to build examples to read our data. Now, when I say read our data, is because the traditional model is to read data from disk, but exactly the same will take place in the in situ scenario, where we have data in memory, we have data partitions, so grid partitions on different MPI tasks, for example, and those MPI tasks will need to interface to the visualization pipeline. And they will do this with this scenario here. So the very first pass here is where the sources advertise the data they are capable of providing. Let me make an example. If I have a large grid of size 1024 cube, I say before the execution of the pipeline, I advertise the fact that the grid is of dimension 3 in space. It has dimensions 1024 cube. It has so many, it has, for example, 2 scalar fields. One of them is the pressure, one of them is the temperature. It has 1 vector field, call it the velocity. There. This is before reading the data, before actually producing the data, I advertise what I'm capable of providing to the pipeline. And this information about the region, the characteristics of the mesh, is propagated all the way down to the sink, all the way down the pipeline. But there's no big computation taking place here. It's only passing down what we call this meta information about the grid. Now, in the case of an unstructured grid, it would be the number of elements, the number of vertices, etc. In the case of a multi-block configuration, you would have the number of blocks. You would have the type of blocks available. Is it structured? Is it rectilinear? Is it Cartesian, etc.? The second pass is what we call the update region, is where the application makes a decision about which region each of the pipeline should take. What does that mean? If I have a large source of data here, and if I have multiple instances of this filter, I can say, if I have 16 pipelines available, I will divide the volume in 16 parts. So this is the information that goes back up the pipeline to the source. At this point of the pipeline, we decide how to partition the data, what region we need. If we understand here that in one of those filters, for example, we need ghost cells, we need to modify the regions of space for the data distribution such that we provide the correct data. So this is the type of information that travels back up the pipeline. And again, the first pass down the pipeline advertises the meta information available. The second pass propagates the request, and those are lightweight computation. And then finally, the third pass is actually the heavy duty. This is where the data is being read from disk, transformed, filtered, etc., until we make the image. Now, all of this takes place rather transparently in a VTK Python pipeline. If you use the ParaView end user application, you actually have the apply button. Every time you construct a pipe, every time you insert a filter into your pipeline, you have to hit the apply button. So this apply button says, I want to force the update of the pipeline. Everything that is connected above me in the pipeline will be executed. We've talked about the VisIt software, which is an alternative for an end-user application. VisIt uses a different strategy where it lets you build up the pipeline. It lets you assemble the full pipeline without having to hit the apply button. And then finally, when you make an image, that pipeline is already fully configured and the execution can start being processed. So there are two approaches, let's say complementary, but always using the underneath the VTK execution model. So this we've gone through. Now, yeah, the main concept is really this vertical, this pushing down data the pipeline. But what you've learned now is that there's actually a two-way communication of events and information. Now, examples of filters and sources, we have them here. I've tried to open up the graphical user interface of ParaView. You have lots of sources here available. And those sources are actually great to make examples of grid which would be similar to what you have, and then try to see what's available given the mesh type. And then filters, you have different families of filters which are available for your data. There we go. So this execution model, as I said, is a mix of event flow and what is the word? Event flow and exchange of information. So it's really a bidirectional environment. And in the VTK pipeline, those would be 4 lines of code which you are going to see in every Python example. The instantiation of a renderer, a render window, and then the command render is actually what triggers the execution of your pipeline. Let's look at a couple of examples here of the of a pipeline. Now, some of the source code I'm going to show on the screen, they are all available in the CSCS folder on the virtual machine. So you will be able to exercise those small demonstrations. Now, the source, this would be, in this particular example, a VTK image data. Now, I've left out some details about resolutions, scalar field, vector field. This is just to show you the bare skeleton of a pipeline, the VTK image data. Then we take a geometry filter, which would be the extraction of the actually polygonal surfaces making up the image. We map this with colors, with wireframe modes, there's a long series of attributes you can map to make the pictures. You create an actor, then you create a renderer, a render window interactor. This lets you actually manipulate the image with your mouse. It lets you pick object, select object with your mouse. It lets you do multiple things. And then finally, you render your image, and then you start the interactor. Now, this perhaps looks a little bit an abstract notion here, but there is a series of examples on the VTK website called VTK Examples. This is the latest contribution of Bill Lawrenson in the USA. Bill has actually converted many of the wiki examples into this repo, which is now available. And you'll find examples in C++, in Python, for most of the standard filters and mapping techniques available in VTK. So don't think that you have to invent all of this from the top of your head. Many examples are available to do this. There's something about syntax that has to be explained in greater detail. The difference between, you're going to see in the examples, the difference between the set input data and the set input connection syntax. When you take a source of data, such as, for example, the VTK image data, which is the Cartesian grid, you apply a geometry filter to it. To connect the pipeline, to build the pipeline, you need to say that the input data of the geometry filter is the grid. And in that particular case, you use the command set input data because ID, the type of that particular object, is a VTK data object, as opposed to a VTK algorithm. And this is basically, I think, the minimum notion that you need to have about the VTK class hierarchy. I will show it in the next slide. You have the VTK data object hierarchy, where you find the VTK image data, the structured points, the uniform grids, the rectangular grids, etc. And then you have the VTK algorithm hierarchy. Those are, if you want, two hierarchies of objects which sit side by side in the VTK toolkit. And those are where you find actually the algorithms doing the data processing, such as, for example, the geometry filter. I'll go back just a second. If you have a data object, you use the set input data syntax, as in the example here. If instead you have an algorithm, if you connect here the polydata mapper and the geometry filter, you use the set input connection syntax. And because of this metaphor of the pipeline where you connect modules to each other, it's natural to say the input connection of one module downstream is nothing else than the output from the previous module, from the previous module in the pipeline. We're going to see this in a more concrete example. All right. Let's build up a 3D Cartesian grid with one scalar field. Those would be the 1, 2, 3, 4, 5 lines of code you need. And with that, you have a Cartesian grid. You declare this VTK image data object. You decide the resolution of your example. So I've picked up here a completely arbitrary number, 31 cube. You decide on the spacing between grid points in each of the X, Y, and Z axis. You decide on the origin of the block of data. So this would be a cube of data sitting in space. In that case, the origin would be 0, 0. You set the dimensions of the grid and that's it. You have a valid Cartesian grid that you can process in the pipeline. Now I'm going to attach some data in a very synthetic manner. I will use a couple of NumPy tricks to generate data for the x-axis, the y-axis, the z-axis. So it's basically here linear spacing of data values along the axis. I use the NumPy mesh grid module to calculate x, y, z coordinates, and then I do x squared, y squared, z squared, square root of, and this will be my data array. Now data here, the name data is a NumPy array, and I'm going to shove that into the VTK Cartesian grid just created above. Now this is a syntax that you need to cut and paste in each of your examples to make it happen. There is a NumPy interface module of VTK providing this interchange of NumPy and VTK array. Basically here I import the module as the name DSA for dataset adapter. I wrap the object Cartesian grid through the DSA interface to get an image object. And on that image object, I have a dictionary called point data. And here I have to make a little parenthesis. If data on a grid, if your scalars and vector fields are stored at the vertices of the grid, they are stored in a structure called the point data. If they are stored at the center of the cell, for example, at the center of a tetrahedral cell or at the center of an hexahedral cell, those would be stored into a substructure of the grid called the cell data. So basically, point data or cell data would be the two means of attaching data arrays to a grid. There is actually a third type, which is called the field data. This is data such as, for example, a Reynolds number, or I don't know, an absolute temperature, one number, 273 degrees Kelvin, or number 42, like in the Hitchhiker's Guide Galaxy. Single numbers or strings or attached to the overall grid, those type of data is stored in the so-called field data. Now, this example here, we store the data at the vertices, so we use the point data array. And we keep appending data with a name. Here I call it scalar because I lacked imagination. There we go. So those are the examples I've provided in the Mesh Builder subdirectory in your virtual machine. You're going to need to load the VTK module. If you're not familiar with the modules interface, this is how it works, and this is what we have on PitchDane, for example. If you do a module available, the command module avail, it will show you all the different softwares, libraries, end user applications installed on the machine. VTK and ParaView and VisIt and ADIOS, etc., are installed on your virtual machine. So if you do a module load VTK, you'll have the VTK Python executable available at your hands. Now, if you're more comfortable, and I actually suggest to use either Python or IPython on your own computer, so that you can interact and go back to the to the main pipeline as much as you want. But basically, VTK Python is your Python interpreter with the Python path set up appropriately already to load the correct VTK libraries. If you're using Python 2, this would be the syntax to load a particular example, exec file, the name of the file. If you use Python 3, this is what I use, exec, open, the file name, read, and close parentheses. And this gets you, this is the same thing, this will execute the full pipeline from source, mapper, and render. And if you open any of those examples, and I've prepared, I think, 6 or 7 of those examples, your job as an exercise is to actually identify the name of the source object, the name of the mappers, etc., and then start modifying some of the attributes of those modules and see how, see what effect it has on the generation of the image. Each of those examples start the window interactor, which gives you access to rotation, scaling, etc., change of viewpoint in your window. If you hit the Q keystroke on your keyboard, you go back to the Python prompt. This is where you have a chance to modify the attributes of your pipeline. And then you start again the renderer, the interactor, to actually see the effect of your changes on your pipeline. So the first example is VTK image data 0.py. The second example is VTK image data 1.py. Nothing has changed except that we've added a scalar variable. There's a second example called VTK image data 2, where we actually color the mesh with the given data array. Now, how will all of this execute in parallel? If you have very large data, and I'm going to insist on this, when dividable, because not all file formats allow a simple partitioning of your data. You know the word legacy, right? There are legacy file formats, very old file formats where to access vertex number 1 million, you have to actually read the first 999,000 vertices before getting to the 1 millionth vertex. So those are difficult to, those file formats where you don't have quick random access to different parts of your data are very difficult to divide. If the data can easily be, if your algorithm, if your reader knows how to divide your data cleanly, in that case, the pipeline will be instantiated multiple times for as many servers you have to execute the pipeline. You have here an article that you can read later on at your desk on the VTK parallel pipeline in the wiki. It's pretty instructive on how this is done. And this is the final part of the 4 examples I have provided. So part 3, VTK image data 3, the only thing I have changed from the previous example is this, the VTK polydata mapper, which is right here. I can give it I can set 2 different attributes of it. I can decide how many pieces I want for the global mesh. In the example here, I say 4. And I say, I want to see piece number 0. And you're going to see on your screen exactly the piece 0, which is 1/4 of the global mesh. Now, you can imagine that the end user application such as ParaView says, okay, I have 4 servers, I do exactly this, I assemble all the pieces together at the end, all of this is transparent to the user. But you as a writer of the data interface between your simulation code and the visualization library, you're going to need to understand those pieces, and now I said the word sub-extents. If you have a Cartesian grid that you divide in 4, if I take the previous examples of the grid being 31 cube, how do I divide that in 4 different parts? Well, 31 doesn't quite divide into an even number, so you're going to make one grid of 15 by 31, 31, and then the second piece will be 16 to 31, okay? And then you can imagine different data distributions. It will depend on the number of servers available. It will depend on how your simulation code distributes the global volume into the different executables. Now, I should probably try to do the demonstrations right here. So help me out here. How do I
the Alt tab, okay, the escape, that works too. Yeah, and now there's the VM. The black window in the back, you'll have to log in. Just click on that.
Wait, I don't see it. Oh, yeah.
And just click on this black area.
Oh, okay.
There you go.
Oh, good. What's the password?
CSCS_password.
Yeah, that's right. All right.
If you're in the VM and you go to screensaver, you'll have to log back in. But the password is CS. CS, this is all lowercase. Password.
All right. I'm going to try to make a rather big font here so that you can all see. Module avail is the first command I talked about. And as you see, we have ADIOS version 1.13 available, Mesa ParaView version 5.41, VisIt, VTK, which is on the other
The font's
side.
too big.
Yeah, it's too big for my screen, etc. Now, the next command to do is module. Wait, I went overboard with my. I'm going to reduce that a little bit. Okay, so here's VTK on our screen. The module VTK version 8.00 available. Very good. I'm going to load this. Why don't I see the bottom of my screen? I need to. Is this font size big enough for you in the back? Yeah, so I'm going to keep that particular font size, and I need to make to reduce my window size so I can fit it. I don't see a resize button. Help me.
It's on the right side. If you move it to the
Yeah, probably. That's because it's off my screen. There we go. It's off of my screen. Let's just actually. There we go. So, module load VTK is the command you need. Now, what does this do? You can actually do a module show VTK, whoops, with a space. There we go. It loads a couple of support libraries, such as MPI, Mesa, ADIOS, and it sets up the correct path, you see, for the LD library path, the Python path, and the path to the binary installation folder of VTK. So we're using Python 2.7. So we have here now the VTK Python executable ready at our hands. Okay. If I run the interpreter here, it tells me VTK version 8.0. And here I have the full VTK library at my disposal, so I can start typing Python command. Now, I'm not going to do it from the top of my head. I'm going to go to the exercise, which is in the CSCS folders, In Situ, mesh. Okay, so this is why you need to do a git pull rebase. There we go. Okay, you've all followed me in the CSCS In Situ folder. I do a git pull minus rebase to pull out the latest contributions, and I now have a mesh builder subdirectory. Now, the convention I've used is that all the file names here, which starts with VTK, those are ready for the VTK Python executable, whereas the PV something Python, those are ready for ParaView Python. So we're going to execute the first one here, VTK image data 0, and then you'll see what happens. It's going to be pretty simple, VTK Python, VTK image data 0, and why is this transparent? I have a transparent background.
It was doing that to me yesterday, so I'm not really sure what the deal is with that.
Let me put it away here a little bit to the dark. There, I have my interactor going here, and I have a mesh. I have a volumetric mesh of size 31 cube. Pretty simple. There's no data attached to it, so I can't do very much with it. I'll do the second version of it. Same thing, basically, but I've attached a scalar field, which I don't see yet. Let's do things a little bit smarter. Let me show you, first of all, the content of image data 2.py. And we're going to go through, yes. Those examples are based on the so-called VTK Python algorithm base. So there's a little bit of syntax here that's kind of heavy. We're going to concentrate on the few lines which are fundamentals. The first is the fact that I'm going to produce a grid of type image data. So this is the output type. Remember, the first pass of my pipeline, I have to advertise the type of data I'm capable of producing. I produce a grid of type VTK image data. The dimensions of this grid is 31 cube. And this will be, you see, request for information, just the lightweight data available. What else do I need? I need the spacing. I need the origin. And I set the global extent, and in the VTK syntax, it's called the wall extent, like this. I set it to be 0 to dims of 0 minus 1, etc. This is because if the number of grid points is 31, my indices go from 0 to 30. Okay? There. And here again is the example of constructing some synthetic data using the square root of x squared plus y squared plus z squared. And this is the command I had already documented earlier. I attach to the object called output the data, the NumPy data array called data, and I give it the name scalar. Now that name is going to be important because I'm going to tell the geometry mapper to color the data with the scalar field called scalar. And here's now our pipeline. I create the Cartesian grid. I use the geometry filter. I set up a lookup table. So this is code I usually cut and paste from different examples. Important is that the range of the colors should go from 0 to square root of 3 because I have a cube of x squared, square root of x squared plus y squared plus z squared. I know that the maximum here, I have hardwired the number. I know that the maximum of the data will be np square root of 3. And I set my mapper. Oops. And there it is. I select the color array to be the scalar label, the actor, the ranger, etc. There. So can we execute this and see? I'm going to use Python 2. I'm going to use VTK Python, which is the same exec file. And my file name. And sure enough, I have a grid of size 31 cube colored by the scalar field square root of x squared, y squared, etc. I haven't put a color legend here, but the blue means the low value, the red, it's the standard color table. There we go. Now, we have here a full size grid. You could count how many vertices I have here along each dimension, and it's exactly 31 cube. Let's go to the last example, which is the script number 3. What has happened here? I can see only 1/4 of the grid, and that piece is piece 0. It has exactly the dimension 0 to 30, 0 to 16, 0 to 16. So I'm actually printing those values here in the Python source code here, so you can actually really understand what is going on. Imagine that the global volume actually sits above it here and up front. And why is this wall here transparent? And why is the upper wall here transparent? It's because it's an internal wall, right? We've taken the global 31 cube volume, we've cut it into 4 pieces, but the cuts are just internal. There's no real surfaces. So VTK actually does the right job of saying these are external walls here, 1, 2, 3, 4, and the rest is internal. Now, the source code was M, the polydata mapper, m.setPiece 0, 0 out of 4. So let's see what would happen if I select another piece. I'm going to make, oops, I want to position it right here. My Windows disappeared. Well, get piece is 0. If I say set piece is 1, I need to show up my window. Where is it? No, it's not that one.
Maybe up above. Do you see in the top bar?
Oh, yeah. Yeah, this thing right here. Yeah. I need to reduce, I need to shrink because I want to show you really effect of, there we go. I need to have them side by side to, what happened to my cursor here? Oh, it's because I haven't stretched. I'll get there. Whoops. All right. We're set. Nothing has moved. This is important because I want you to understand what's going to happen here. This is P0 of the volume. I've set now, I've asked the pipeline to deliver piece 1, and all I need to do is remake the image. There we go. Did you see the switch? You were not looking, perhaps.
The text is off the bottom of the screen.
Yeah, I need to stretch again. Oops. I'm having difficulty knowing how to stretch this. Okay, I'm almost there. All right. Let's do it again. Set piece 2. And here, by saying when window dot, by calling the render method render, I force the execution of the pipeline. So if you all watch now carefully, except for the syntax error, there we go, this piece 2. And you see that the extents have changed slightly. That piece above is of size 030, 016, 1430. And anyway, if you do all 4 pieces and you add them up, you'll see that it actually covers the full volume. Yes, question?
I have 2 questions. The first one is, how do we switch between the
Yeah, so this was in the notes. You have the object called iRan, which is the interactor. The interactor lets me animate here the viewpoint, etc. of the object. With the Q command on your keyboard, you exit and you go back to your Python prompt. And when you want to restart, again, you do start. So let's do the final thing, the final example. I'll do set piece number 3. And I'll render. And here I have set piece number 3. I'm getting here a little bit of a clipping effect, which by resetting the camera, I'm going to fix. Oops, I need to restart my, where is it? Why does it not show up in my history? I don't know. I ran that start. There we go. All right. There is basically all for this morning. We have, for this example, we have demonstrated that we have at disposal a global Cartesian grid of size 31 cube. We want to pass this to a parallel pipeline, which is going to use 4 partitions of my data. The data gets partitioned automatically, by the way. I did not have to compute those different indices. The VTK execution engine, knowing the global size of the data, decided by itself, okay, I know how to divide that particular grid in 4 pieces, and those are the 4 pieces. Now, those 2 sets of informations, the global dimensions and the local dimensions of your partition, is what we're going to put in our example to couple the mini-app solver with the SENSEI data bridge. Building up the data bridge, writing the source code for the data bridge is going to be exactly like this, defining the type of grids we have, defining the global dimensions, the local dimensions, the name of the scalar variable available, give a pointer in memory to the data variable, and this is basically the skeleton of the data interface. We'll stop right here. We'll take a break right here. Yeah, questions?
What that defines how the data is displayed in 3D, because it's displayed as a surface with a grid.
Yeah, in this case, the module called VTK geometry filter actually extracts the outside surface of the grid. Okay, so we only see the walls of the grid. If we wanted to look inside, for example, with a volume rendering filter technique or with an ISO surface, we would actually see the data inside the volume. Okay.
And so this VTK point data anchor is the one that's...
The VTK geometry filter is the first filter in the pipeline which extracts the outside surfaces. And the mapper, if you want, for every geometry filter, you need to have a mapper. It's a conversion from an internal object to a polygonal object that is ready to make an image, basically. Now, I said that the syntax was a bit complicated for the VTK Python code. That same example is available as a ParaView Python script, and that is simpler in size, much reduced. It has the same fundamental commands: set spacing, set extents, set dimensions, etc., which are necessary to build the grid. And you are welcome also to exercise that particular. I'll just show you before the pause. I'll show you how to actually do it, and then we'll pause. Where's my cursor? Exit. If I do module load ParaView, module avail, does it have a...
Oh, hey, Jean,
Yes?
and everybody actually. So when you're doing these modules, like some of them conflict with each other. Like ParaView comes with its own copy of VTK. So I would recommend just closing that terminal and starting a new terminal.
Yeah.
Or either that, or you could do the module unload VTK and then module load ParaView.
Yeah, this is actually what I've done here. Module,
Okay.
With a typo. So module unload VTK would do this, and then I did a module load ParaView. Now I've told you that the PV examples are for ParaView, so if I execute this as script, I'm going to have exactly the same, and I'm going to execute it like this: minus script equals PV You can tell I don't have the keyboard I'm used to. There's ParaView. There's my grid. It's hard to see because there's no wireframes. I'm going to change the representation of it to surface with edges, and there is my 31 cube grid, which I can color with the scalar field called scalar. The colors are different because the default here is blue to red in this particular setup, but you can use any color map you want. The Python script, which we've talked about, appears right here in this little window, which is the Python programmable source of ParaView. It's a lot of source code already. We don't have to look at every line of it. This is something for you to, at peace, later on next week, you can study both sides of it and play with it and change the parameters, and you'll see that it actually works. Okay? There, we'll take a pause. And you can, of course, drink coffee and ask questions during the pause.